Good evening to you, Year 12 pupils, and welcome to the last AS session on chemistry. It is tonight being led by Mr. Black, who's been supporting me last week, and he will be taking on the subject of rates. As always, I will be available to answer any questions that you have via the Q&A section if required, and please do so if you've got anything at all. But otherwise, I will stop talking and transfer you to the capable hands of Mr. Black.
Hello, Year 12. Well done getting to this point. Hopefully you've watched all the sessions. Just Miss Stevens, if there's any issues with sound like last week, if you could just let me know.
Of course.
Thank you very much. Okay, right. So yeah, we're going to be looking at rates of reaction. You know, as with all your topics and Year 12, this has a massive link into Year 13. So this is the groundwork for Year 13 chemistry as well. So not just important for your assessments if it comes up, but also important for your Year 13 chemistry. So let's move on. We'll start looking at the GCSE aspects really, and then we'll move it in towards A level. So rate of reaction. Hopefully you know that what we're looking at here is how quickly something gets used up in a reaction, or how quickly something's actually made. One of those is more useful than the other, and we'll talk about that later. Okay, so rate is how quickly something's used up or made. So the first thing is then, how do we monitor rate? Okay, so we've got a reaction here between magnesium hydrochloric acid, and when you're looking at how to monitor a rate, you need to look at state symbols because they give you a big clue about how to monitor. And if you look at this reaction, as you can see, we're producing a gas, okay, which you can see with this fizzing or effervescence. And that allows us to actually monitor the rate of the reaction. And that's done by gas collection. All right, so there's two ways we can collect that gas. There's this one with a gas syringe. And actually, I prefer this method, which is collecting underwater, okay? And both techniques work really well. So that's how we can monitor the rate. We collect the gas over time, and that produces a rate curve. All right, so this is the typical kind of curve or line we'd expect to see in a rate of reaction. And if you did GCSE rates in Year 10, I know my Year 10s, that was one of the topics we didn't actually teach. I'm sure you've covered it in your A-level lessons now. You should know the steeper the curve, the faster the reaction, and you should also know that your fastest or steepest part of your curve is at the start. Okay, and then you should also know over time, as you can see there, the curves are line curves. Okay, and that indicates the reaction going slower, and eventually it goes horizontal, it's flat, we're not producing any more gas, and surprise, the reaction is finished. All right, so those are your points on the curve. So that's kind of GCSE really. All right, now at GCSE as well, maybe even at A level, you would be expected to know from that curve at which point the reaction is finished. So it's a fine line, but basically it's where it's gone flat. All right, you're not producing any more gas because the reaction has finished. One of your reactants has been used up. So here's the reaction. How could we monitor the rate of this reaction? Well, again, we can see a gas. We've got carbon dioxide. So we could use our methods that we've discussed earlier. We could use gas collection, those two methods there, which I've shown you again. However, with a gas like carbon dioxide, there is another method, and this is where we can weigh the reaction. Now, it does say magnesium hydrochloric acid here. Obviously, I'm talking about calcium carbonate and hydrochloric acid. I'm going to come on to this in a second. I have an issue with it. Just pointing out here, we have a cotton wool plug in the flask. This is to stop splashing. We don't want to lose mass because we're losing a reaction mixture, but it does allow for the gas to escape. And as you'd expect, we'd see the mass of our flask contents decreasing. We're losing atoms as that gas. And what we would really do, we want to really plot the mass of the reaction. We want to plot the mass of the gas being produced. And you can see here the calculation that we've done. We start off a mass of 156, and I'm just subtracting the subsequent masses to work out the mass of gas produced after each minute. And again, we get this curve here. All right, so that's another method for monitoring rate with a gas. If you're not going to collect the gas, you can weigh the reaction. Which brings me on to this. Now, I just looked for a stock image off Google just to show you, weighing a reaction. This would not work. This is not a good method. Now, you might be wondering why. We do produce a gas, but that gas is hydrogen. And the problem with hydrogen, as you know, it's got a low AR value or MR value. So it wouldn't, the mass loss is not big enough to actually record it. So I wouldn't recommend this method for this reaction. Hydrogen's too light. So this would have to really be done as a gas volume. Okay, so not a good choice. So what do we do with these curves then? Well, what we do is we take a gradient of the curve. And what that gradient does is it tells us our rate of reaction. Now, hopefully you're good at taking gradients. I think it's a skill. I think it's something that you definitely need to practice. So if I was you, I'd look at on the question bank rates and try and practice those taking gradients. So, you could be asked to take a rate at various points in the reaction. So I've chosen a specific time here. Okay, so I've come up to the curve, and what we do is we take a tangent of that curve. So that's my tangent, practice drawing them. There is a bit of leeway on how you draw your tangent. Okay, so examiners won't have an exact value. There'll be an area of, difference that you're allowed. And to find your gradient, all we do is we do delta y, so the change in the y-axis, divided by delta x, the change in the x-axis. Okay, so these 2 points here. Now, I always tell my students, when you take your tangent, don't make a small tangent, make it big. You make it as big as you can, and also try and get it to line up on points on the axes that are easy to work out your delta y and delta x. So if we want to work out our rates, we've got delta y over delta x. I always kind of just double check myself that I'm the wrong way around. Okay, and in this case, our unit of rate would be grams per second. So I've written it in both formats, G over S or G over GS to the -1. Okay, so you've got your change in mass and your change of time. Initial rate. So initial means at the start. All right, so this is where we take the reaction, and this is probably the most important information we can get from a rate graph, and you'll see this in year 13. This is the reaction at the start. It's when the curve is at its steepest. So when we take our initial rate, we just extrapolate that straight line, okay, before it starts to curve. So our delta y would be in this region over delta x. Now, so far, our curves have all been involving the formation of product. Okay, as you can see, getting more and more products forming. Actually, in year 13, we don't really look at how much products formed. We're much more interested in what's happening to the concentration of the reactant. And when you get into year 13, you'll see why. It's to do with finding something called an order of reactant. And you can only do that by looking at the change in concentration of the reactant. Again, we see that classic curve here. All right. So what's happening here is at the start of this reaction, where we've got a high concentration, as time proceeds, our curve is getting less steep. All right, so our reaction is slowing down. The steeper the drop, the faster the change in the rate. So you can see here a massive change in our concentration at the start, much lower as time proceeds. So if I was to take the gradient of this curve, it's exactly the same as we've done before. It's delta y over delta x. You can see I'm doing the initial rate here, so I'm finding the steepest part of the curve. There's my delta y and delta x. And I can't believe how bad this scale is. I was trying to work out the intervals. It's And going up in 0.4s isn't something I choose to do myself. I'd be going up in 0.5s, but hey, there you go. I had a bit of a head scratch when I was trying to work out, you know, the delta Y and delta X values. It's been a long week. Please don't look too closely. So there's my delta Y, and there's my delta X. Delta X, I could do. Yeah, delta Y is scratching my head a little bit. So those are two values to work out our rate. There we go. Okay. Hopefully you can see something missing from here. There's my answer. I wonder if you can spot what's missing. Well, hopefully you've decided that the units are missing. So our units here, again, you know, it's the change in concentration, mole dm to the -3 over time. Okay, so that is our unit. And that's the unit we usually associate with rate. You know, if you're looking at gas change, a mass change, then it would be grams per second. But usually we're looking at change in concentration because that's much more useful. So that brings us to the question, why do our lines curve? Okay, well, the reason our lines curve is because of collision theory. Okay, just by the way, I've just put here a little thing. What is rate? You know, if you ever asked to define what rate is, you know, exam boards do ask this all the time. What is rate? That is what I would say. I would literally write that expression: rate equals change in concentration over time. Job done. Move on to the next question. All right. So it's, you know, and I know it doesn't sound like it's not a sentence as such, but you have defined what rate is. Okay, and there's your unit of rate, and that's really important for year 13. So why has our, let's just go back, why has our curve, or why do we produce a curve as we monitor change in concentration over time? Well, as I say, it's because of collision theory. All right. As this reaction proceeds, your reactant is being used up. And what that means is there's less of it in your reaction mixture. In effect, the concentration of a reactant decreases over time. Now, using collision theory, you should know that with a high concentration, you have lots of particles in your solution. So I've got a solution here. I've got a solvent maybe, and I've got a reactant A and I've got a reactant B. And you can see here I've got a low concentration of reactant B. And if I was to increase the concentration, I would have more of those particles in that volume. So now you can see I've got high concentration. And hopefully you can remember that that's going to result in more collisions. But we have to be careful how we talk. And I'm just pointing out here, by the way, you know, when we talk about concentration of a solution, it applies to a gas as well, but this would be in terms of pressure. So if you have a high pressure, it's equivalent to having a high concentration of particles. So let's talk about exam answers. Wait a second, there is it. There we go. I've skipped it into a slide. This is, if I'm ever asked about why concentration affects rate, this is what I respond with. And there's two really important things we put in our answers. You have more particles, but you can't just say there are more particles of a higher concentration. You have to say per unit volume, or per decimeter cubed, or per centimeter cubed. I don't care what volume you use, as long as you refer to that there are more particles per unit volume. And that results in more successful collisions per second. All right, this is about rate. So this word per is going to be in your responses. So I'm just going to go back to this now. This is what's called a rate equation, and you look at this in a lot more detail in year 13, and I'm not going to go there too much at this point. But you should appreciate that rate in this rate equation is proportional to concentration. Okay, now when you're in year 13, you'll see there's an indice value here. I put n. That value can either be 0, 1 or 2, and that's called the order of a reactant. And you find out all about that in year 13. And it just basically tells you the effect, how big an effect the change in the concentration that reactant has on the rate. But for you guys, At this point, I would just say, be aware of this rate equation and just know that, your rate is proportional to your concentration. Higher concentration, higher rate. This thing here, this is called your rate constant, and we'll talk about this in a second. So in year 12, they may give you a value of the rate constant, they may give you a concentration, they may give you an indice value, but I don't tend to see it in year 12. This is more year 13. So there you go, more successful collisions per second, more particles per unit volume. So what are the other factors then? Well, the other factors, hopefully are your temperature, your surface area, and the addition of a catalyst. And so we're just going to run through those now, just quickly. I'm not going to read this out to you. I'm just going to point out that for a reaction to take place, your particles have to collide. And not only do they have to collide with sufficient energy. So if you had two particles, I'm not sure if I'm on camera now, and they collided like in this direction, they'd probably just bounce off and not react. If you had two particles come in head on at sufficient energy, they would react. And you can see we're trying to break the bonds and form our new ones. And that energy you need from those collisions is called your activation energy. So we'll come back to that in a moment. So let's look at temperature then. Okay, raising temperature is always going to increase the rate of your chemical reaction. And if you remember your lesson on equilibria, increasing your temperature, increase the rate, isn't necessarily good for your yield. But you're always, whatever you do with temperature to improve your yield, if you increase it, your rate's going to go up. If you decrease it, your rate's going to go down. Okay, why is it then? Well, it's to do with the energy of the particles. Your particles have more kinetic energy at a higher temperature. So if you have a look here, we've got particle B, and I've got a low temperature here, and you can see particle B has got, moving around, it's colliding with particles. Hopefully one of those collisions would have been successful for the reaction. And if we did it at a higher temperature, you'll see that your particle is moving faster, you have more collisions per second. Okay, so go back. There's a couple of things we need to talk about when we talk about temperature and the effect on rate. So A, you get more collisions per second, but not only do you get more collisions per second, a higher proportion of those collisions are successful, i.e. they result in a reaction taking place. So let's see. You should recognize this. This is a Boltzmann distribution curve, and what this does is it shows us the distribution of energy of our molecules. And you can see here at this, most of our particles at this particular temperature, T1, you can see at T1 most of our particles have this kinetic energy, okay, and very few of our particles have this kinetic energy. Okay, so a higher kinetic energy. So most of our energy of our particles is down here at the bottom. Okay. Now what I've marked on here is our activation energy. These particles here have sufficient energy that when they collide, they will react. All right. So I'm not sure why it's not marked there. I usually have a EA marked on here to show where the activation energy is, but this is our point. Below this point, any of these particles don't have sufficient energy to react. And what I'm going to show you now is if I increase temperature, what happens to the distribution of energy? Well, as hopefully you know that your particles, more of your particles will have more or higher kinetic energy. And that happens to your curve. And the way I see it is, I see it as almost like rolling out dough. So you can imagine rolling the particles or flattening this out, you're flattening the curve. And what I always say to my students is the area under those two curves has to be the same. All right. Now, obviously, when you're drawing your diagram, that's going to be difficult to do. Okay, but it is definitely worth being aware of. I would practice drawing that diagram so it looks like the diagram. Okay, so this is the kind of diagram we want, and you can see there EA. Okay, so this is the one we're particularly looking at. We've flattened our curve out. The area under the curve is similar, okay, because we've got the same number of particles. It's just now more of our particles have a higher kinetic energy, okay. So Very, very important to be able to draw that curve. I'm not going to leave that there. You can read that in your own time. But what I've put is, the effective temperature is that you increase the number of collisions and you increase the proportion of the collisions that meet the activation energy. Okay, now we're going to go back to the rate equation. You'll see this in year 13. Temperature affects this value here. As you increase temperature, this is what we call the rate constant. And in year 13, we look at how we can find this value. But if you increase temperature, the effect is to make that value bigger. If I make that value bigger,
We can't hear you suddenly, Mr. Black. Still can't hear you.
can you hear me now?
We can hear you, Mr. Black. There we go.
I have no idea what happens here. I'm so glad not to be online teaching anymore. No. Right, okay. Sorry guys, let's get back in. So another factor that affects rate is surface area. So you can see here I've got a solid and here's a particle. Now this particle can only react by colliding with the particles at the surface. That means the majority of our particles aren't able to react with it. So what I can do is I can break my solid up. But can I react with those ones on the surface? So I'm going to break my solid up now. And by breaking my solid up, what we're doing is we're increasing its surface area. All right, now we've got more particles to collide with. The other way you can increase surface area, by the way, is not just grinding it up and making it smaller. The other way you can increase surface area, of course, is just by putting more solid in. So instead of using 1 gram of magnesium, if you put 2 grams of magnesium in, obviously you've doubled the surface. All right, so that's going to lead to your rate increasing. So it's funny to think of something smaller having a big surface, but it's a size surface area ratio. Okay. Now this brings on to our final factor. This is obviously very important for us, and these are our catalysts. And you'll hear this word all the time. These are substances. Now, again, definition, you can make your own up if you wish. I wouldn't, I'd learn one. And just make sure you're comfortable with it and that you can recall it. So what's a catalyst? Well, there's various things I would say. They obviously speed up chemical reactions without undergoing any change themselves. And what that means then is that they won't get used up during the reaction. So if you use 1 gram of catalyst at the start of the reaction, by the end of the reaction, you'll have 1 gram of catalyst. Think of a catalytic converter on a car. They can be attached to the car as long as you don't poison the catalyst. They'll be around for a long time. So how do catalysts work? Well, unlike temperature or surface area concentration, it's not going to increase the number of collisions. What it is going to do is going to increase the proportion of those collisions that are successful. All right, so how do they do that? Well, they lower the activation energy. And the next thing I'm about to show you is obviously very important for you. So here's an energy profile diagram. Here we've got potential energy, or enthalpy. And I'm just going to ask you to look at reaction just very quickly. It's not related to what we're doing today, but it doesn't mean it's not important. Exothermic or endothermic, this reaction? Well, hopefully you've said endothermic. Okay, you have to increase the energy of the product. Okay, so what I've done here then, or what I've pinched off the internet, is showing you the uncatalyzed reaction. And you can see here there's a big hill to get up. All right, so you're going to have to put in lots of energy to go from reactant to product. That means your collisions are going to have to release lots of energy. Okay. What a catalyst does is it provides an alternative route where not as much energy is required. So you have a less energetic collision, resulting in reaching this point. And again, you know, we're going to have to be aware of the Boltzmann curve. So you can see here a Boltzmann curve. Again, we've got the distribution of energy. Most of our particles have this lower energy, and the effect of the catalyst is to lower the activation energy. So if you think of this on the Boltzmann curve, now I've shown this with this line, this region here would also now be shaded blue, which I couldn't do with paint, sorry, but you get the idea. And now we can see lots more of these particles now will have sufficient energy that when they collide, they will react. Okay, so that's the, you know, two really important curves: the one with the temperature and the one with the catalyst. And as I say, I would practice drawing those. The effect of a catalyst then on the rate equation, they increase the value of K, right? So they make this value bigger. It's called the rate constant. And as I say, do not worry about the rate constant till year 13. Okay, so I'm just going to do a little bit of a summing up on the curves at this point. I'm not going to spend too long on it. You can work for the PowerPoint and have a look at this, but I just wanted to kind of do, it's more of a GCSE thing really, but it's still important. And just, you know, we've got 5 grams of magnesium in excess hydrochloric acid. They monitor the rate, okay, or the, you know, the volume of gas over time. And you can see here it says how long the reaction takes to finish. 6 minutes, maybe 7. Oh, there you go, 6.5. Okay, and then, you know, what would it be like if we did this at higher temperature? Well, we get a steeper curve, but the volume of gas we produce is the same. Okay, we still make the same amount of gas, just in a short time. And quite often when I see people do this question, you'll see that people will do a line like this. So it's good that it's steeper, but where's the extra gas coming from? Okay, so I'm going to move on. I'm not going to spend time on that. There's more important things for us. You can work yourself through that one. So we're going to look now at a reaction that is commonly asked for in the year 12 papers. It's a reaction between thiosulfate and hydrochloric acid. So first thing I'll ask you to do is just, how would you monitor this rate? How would you monitor that rate? Well, I'll tell you what you're not going to do is you're not going to collect a gas. Right? This gas is soluble, so it would actually dissolve in our solution. So no bubbles of gas are seen in this reaction. Even though it says, you know, sulfur dioxide gas forms, it dissolves in the solution. So you're not going to be able to monitor the formation of the gas. However, there is something that allows us to monitor this rate. Okay, and that's that we've got 2 aqueous solutions being mixed together. So we've got 2 clear solutions, and when they're mixed together, they form a solid, better known to you as a precipitate. And that means your reaction is going to go cloudy. So I've got here, you know, typically what you might see over time. You'll start with your pure, this being the start reaction, and as time proceeds, it gets cloudy and cloudy. You can actually see the precipitate here in this one. Okay, so that is how we're going to monitor this rate, formation of precipitate. Okay, and I'm just going to go through the 2 ways that are allowed to monitor the rate. So the first way is using technology. You could use what's called a light sensor, and I hope you appreciate that as the precipitate forms, less of this light is going to pass through the sample. All right, as it gets cloudier, the light's going to start bouncing off our precipitate. So we're going to record less light on our light meter. We can also use colorimetry, and I'll talk to you about that towards the end. I want to focus on this. Okay, so that's what we get. We start off with lots of light being passed through our sample. As time proceeds, less and less light passes through. Again, you know, steep at the start, okay, fast rate slowing down, okay, so you're forming less precipitate, so the change in light intensity is dropping off, and eventually our light intensity drops off completely. So our reaction's probably finished around this point, okay, probably even here really. Okay, so they say that's one way of doing it. What would the curve look like if we used a high concentration of the acid or the fire? High concentration, more particles per unit volume, more successful collisions per second. So we'd expect our curve to be steeper. Okay. So that curve as well, your steeper curve would be if you'd used a catalyst in the reaction or you'd found some way of making it go faster. Okay. Obviously, you can't change surface area of reagents that are aqueous. Now, this brings us on to probably the way that you would monitor rate. Okay, so the way you monitor rate, it's not very high tech at all, is you put a cross down. All right, so you put a cross on a piece of paper and you do the reaction on top of the cross. Okay, so let's say you wanted to look at the effect of temperature or concentration. You would put your reaction over that cross at your different temperatures or your different concentrations, and you would time how long it takes for that cross to disappear. Okay, so it's my dodgy animation here now. So there's your reaction mixture. Your solutions are actually colourless at the start. There's no precipitate. Okay, so you can clearly see the cross. There's nothing stopping that. And then you start the top clock, and over time, like magic, there you go, your cross disappears. You stop the clock and record that time. Obviously not in minutes and seconds. You'd have to convert that into seconds. That would be 83 seconds. Okay, so the less time it takes for that cross to disappear, obviously the faster the reaction. And you'd get a curve like this, which is very nice and tells us quite a lot, but there's something that we can do that's much more useful. We could take gradients of this, of course, to tell us the rate. But to be honest with you, at A level, we won't be doing it that way. All right. We will use the same technique. So you can see here with your low concentration, it's taking longer. With your high concentration, it takes less time. So this kind of way of monitoring the rate by timing an event, we call it a clock method. All right. So what we do in a clock method, we time an event. So in this case, we're timing the event of how long it took for our cross to disappear. And so to work out our rate, what we do then, obviously less time means faster rate, but that wouldn't look right. So what we do is we do 1/time. So if your event is small, doesn't take long to occur, you'll get a bigger rate or higher rate than if your time takes a long time to occur, because you're dividing by a bigger value. And our unit, hopefully you know what your unit is. Your unit would be s to the -1. So this is what we call a clock method. And that's what our curve would look like on a cross method. Okay, well, not a curve actually. So you can see here it's temperature, sorry, as this is concentrations increasing, our rate is increasing. You can't see it very well there, but it says 1/t. All right, so that's our timed event. And the classic one we talk about with a clock method would be, well, it would be the fire sulfate one. That's pretty classic. And we've also got this what's called the iodine clock method. So what we've got in here, we've got our reaction between, hopefully you can see, hydrogen peroxide and iodide ions and your protons. And one of the products we form here is iodine. And so what we have in our solution is we have a little bit of starch. And you only need a very, very, very small amount of iodine to form. It's like a ridiculously small amount of iodine to form to get this really intense blue-black colour. There are little technicalities with the iodine clock method. They put fire sulfate in there. That's to mop up iodine. So because the iodine, if you didn't put fire sulfate in there, the blue colour would be straight away, almost instantly. So they put some fire sulfate in there to mop up iodine as it forms. Makes it kind of the event take longer, and don't worry too much about that. Okay, so then the other way we can monitor rate is what's called colorimetry. Okay, so colorimetry, it's let's say we go back to the fire sulfate reaction. It is what it says. You're looking at the change in colour of a reaction. Now, obviously, colour is to do with wavelength of light. So what we can do is we can look at how the wavelength of light changes over time. So if you've got a coloured reagent, so what sort of things might be coloured reagents? Well, iodine is a classic. If ever you see iodine in a reaction and it says, well, how could you monitor this rate? You would go for colorimetry. If it ever tells you in a question, this reagent or this product is coloured, you're going to use colorimetry, okay? It's leading you there. So iodine is a really good one to look for, or if it mentions, for example, it says, I know nitrogen dioxide is light brown in colour, how would you monitor the rate? Colorimetry is going to be your method. And I've put a little clip here for you to follow, and that goes, it does quite a nice job actually going through the technique and sort of reactions that might use colorimetry. Okay, so, you know, that's your kind of theory on rates of reaction. I'm just going to go through now, you know, some of the things that if you're asked about monitoring a rate of reaction, let's say I wanted to look at the effect of temperature, I wanted to look at the effect of concentration or surface area, we have to have that awareness of what other factors can affect the rate, because all those other factors are actually going to be your control variables. So for example, if I wanted to look at the effect of temperature, I would have to make sure that my solutions are the same concentration. If there's a solid involved, it's got to have the same surface area. You can obviously only change one of these variables at a time. Okay, so that's really important. Also, you know, if you're doing the cross method, it's also important. And normally I say to my students, don't worry about equipment, but with the cross method, if you've got different size beakers, that's obviously going to affect the depth of your solution. So that would also be a factor. So you'd have to have the same kind of beaker being used. Okay, because obviously, you know, your cross would disappear quicker if they've got more solution to look through. And also, you know, with that method, you would have to have the same kind of cross because a darker cross would be present for longer. Okay. So I'm finishing off now by just talking to you about the use of data loggers. Which is better, a data logger? Well, obviously, but why is a data logger better? Well, it's reliable, okay? Anything that has judgment involved, for example, judging when that cross disappears, is prone to error, all right, human error, all right? The one way, if you haven't got a data logger and get around that, is you have one person who judges when the cross has disappeared, okay? So you won't probably get use of a data logger because they're too expensive, so you will rely on that. So, you know, I finished a little bit early actually, 2 minutes. So I hope that's cleared things up for you on rates of reaction. Just wondering if you can go back and see if you can work out your rates. I don't know if there are any questions, Mrs. Stevens, that need addressing.
No, no questions.
Okay, there you go. Well, there you go. Have a quick look at your gradient there. And like I say, you know, I would really practice taking your gradients. And there are plenty of questions you've got on the question banks where you can see, you know, whether you're taking your gradient correctly. And like I say, if you look on this gradient here, I'm just filling time there really, guys. You can see I've chosen points where it's easy to read what the change in delta y and delta x is. All right, well, I'm going to finish there then, year 12. I'm not going to waste any more of your time. We've got 1 minute left. So, yeah, that's it. End of the session. Well done. Thank you for attending. And I hope I've cleared up a little bit of rates of reaction for you.
Thank you, Mr. Black. And just to reiterate some of the messages earlier on, hopefully you've had time to watch all the sessions and found them beneficial. So now it's just wishing you good luck for the coming weeks, really, when I'm sure you'll be undertaking a few assessments. So thank you.
Thanks, guys. Bye.